My name is Tomek Zawadzki. I'm from Intel, working on SPDK. So incoming talks will probably focus on how to transfer data efficiently out of the network. But guessing most of you have the data somewhere stored on your servers. And SPDK is addressing this gap of getting the data in and out of the drives as efficiently as possible. Throughout this talk, I'll give a brief overview of the SPDK and sample use cases. And why did we choose to integrate with VPP for network-related storage protocols, and how to get you started on using both of those. Yeah, so the challenge. Why SPDK exists? So at the very beginning, we had AGDs that had very big latency overhead on the media itself. The software for the driver and the controller were minuscule compared to what media had. As the media improved, the latency of the drives themselves decreased. Meaning that with SSDs, using SATA and NVMe, we got to around 1 to 8% of the overhead just from the driver. But as we went to even newer generation of media, the overhead for the kernel driver became even up to 50% of the latency for the whole solution. This obviously shows that the software for the kernel driver started to become the bottleneck. And reaching the point of 30 to 50% of the overall latency overhead, this became the problem that was worth solving. That's why SPDK exists. SPDK, Storage Performance Development Kit, is a set of user space libraries and reference applications that through lockless and port mode operation allow to reach up to millions of IOPS per core. Of course, due to what was shown on the previous slides, it's primarily designed for non-volatile media. Set of functionalities that extend beyond just the user space driver, enabling different protocols for network and virtualization storage exposure, are included in SPDK. SPDK is open source project licensed under BSD. Having those reference designs and software allows users for a faster time to market using what's already available in SPDK. This is a brief overview of the whole SPDK architecture. It contains a lot of storage-related protocols. From the bottom, the drivers, what's getting the data into SPDK, and at the top, the storage protocols getting them out. What we will focus during this talk is iSCSI target and its integration with VPP, as well as future enhancement of NVMe target using TCP transport, which was recently ratified as a specification and was added to SPDK, but so far using only POSIX APIs. So I'll present two use cases for SPDK. First, basically exposes the NVMe drive to our abstraction layer of BDEV, that we call, enabling some third-party additional BDEVs doing caching, deduplication, and whatever secret sauce a company wants to add over there, and later exposing exactly that through the network, through the iSCSI target. The other one is getting the data from the network using, as an example, NVMe over Fabrics initiator, which splits the provided device into to logical volumes. That's another type of BDEV that we have, and expose that to the VMs directly through vhost target. This allows for dynamic provisioning of the devices, as well as the vhost itself decreases the guest latency, thus improving the VM density. So VPP and iSCSI target integration. So using POSIX sockets for data actually partially negates the benefits of having SPDK being wholly in user space. Because as soon as you reach that point, you need to interact with kernel. This means that you have syscalls going to kernel and back, as well as there's reliance on interrupts within the SPDK iSCSI target. So we chose to search for a user space solution to replace the, or add as an alternative to POSIX sockets, and we came across VPP, which adds exactly that, but keeping everything in user space from top to bottom. So just a brief overview of the net framework abstraction that we use to provide different sets of API, both from the bottom and from the top. So this net abstraction that we use in iSCSI target basically interacts with POSIX sockets and VPP at the same time in runtime. The POSIX are available, they're not replaced by VPP, just as an addition, and VPP support has to be compiled in, since that's external dependency. And in the future, we plan to integrate that with NVMe target using the TCP transport. What I'd like to mention here is that it's written VPP API. At the beginning of the year, we were using VCL APIs, but later on switched to Session API because SPDK is heavily multi-threaded and can handle polling the queues from Session APIs directly. So right now, we leverage the Session API benefits by simply polling the message queues on our own. And what we achieved with that was that SPDK iSCSI target now uses the APIs provided by VPP. We no longer have the kernel syscalls. We achieve a better CPU utilization and enable users to get access to all the networking capabilities that VPP has by itself. A thing to note is that VPP and SPDK work as two separate processes, and thus we opted to use the binary APIs and interact via shared memory between those two processes. So the next steps for SPDK and VPP integration would be to enable Session API callback-based mechanism. This relates to the network abstraction, which for a very long time was based on just using the POSIX sockets and required changes in both the network abstraction and iSCSI target by itself, since it didn't anticipate that at the beginning. So that's change that is coming, as well as for NVMe over TCP with VPP. So how to get started? All of this is available on the SPDK repo right now. All you need to do is just build SPDK with VPP support and start and configure the VPP however you want. And from that point onward, you can use the SPDK iSCSI target with VPP. All the configuration details are available on our site, SPDK.io, specifically the iSCSI target configuration guide. So, SPDK community. We have all of our code on GitHub. We do public reviews using GitHub. You can see what's coming via our Trello. If there are some things, you can pick them up, smaller and bigger tasks. You can reach us via our mailing list and IRC in real time. We hold weekly calls and multiple meetings throughout the year, both developers meetup as well as summits in US and PRC. Of course, first place to head to is SPDK.io. And that would be it for the VPP and SPDK integration between the two projects. Yeah.
Good job ending with plenty of time. Yeah. So we've actually got some time for questions. So we have got about 5 minutes for questions if folks want to ask them. So yes, Ray. Oh, wait, here.
So counterintuitively, I'd say, TCP for storage, you've got a large buffers, so there's lots of opportunity to amortize the cost of a syscall across a large buffer. So why did you? Intuitively, I'd say the cost of kernels using the Linux kernel wouldn't be that high, but there was clearly a motivation for you wanting to change to a full user space implementation. What was the bottleneck or the inefficiency that made you want to change to a user space implementation?
Yes. So when you explore how the POSIX is used within SPDK iSCSI target, you can basically see that almost up to 70% of the CPU usage per core was spent in kernel just doing the polling, the continuous epoll throughout the operation. This, as well as in the NVMe driver case, shows that kernel was the bottleneck here and is definitely a case to look at. And that was our motivation, and still is. Yes?
Cześć Tomek. Chciałem się ciebie zapytać, jak lubicie VPP? Sorry, I translate to the Anglophonics. The question is, I understand the SPDK team is using VPP TCP stack, and the question is, how do you like VPP?
We do like it. There's definitely a lot of work going between both projects. We're working closely with Florin and addressing everything that we can throughout our work together. Yeah, sure.
So you mentioned that VPP and SPDK are two different processes currently?
Yes, that's correct.
Is there any reason for that design?
So basically, we had iSCSI target as a reference application for doing, iSCSI, right? iSCSI target. The user can change it, modify it, do whatever he wants with it. And here we came up with this, that either we would have two separate processes communicating with binary APIs, or one or the other, VPP or SPDK, would need to be integrated into the other. This amounts to a large amount of additional work and design how the two projects work together. This simply was the simpler solution to address this issue.
Okay. So, sorry, one more question. I believe SPDK has a TCP stack. Is that right?
No, that's not correct. That's basically what either POSIX and or VPP is doing for SPDK. Right here, SPDK ends at iSCSI target level, basically implementing the iSCSI operation, either using the POSIX sockets or VPP APIs. We do not have a TCP stack inside of SPDK.
Okay. All right, and one more question from Maciej.
So I have a related question. I'm going to stick to the English. In FD.io SysIt, we do TCP stack tests for VPP, and as you will see from my talk later, they're very basic. we have been really waiting for the opportunity to do it properly. And we currently have Intel x86, Xeon ARMs, Xeon and Atoms. We have ARMs in the lab. And it would be awesome seeing you two guys here and the Intel and ARMS team if maybe we could talk in later on how can we showcase the best of breed in terms of the TCP stack across this both quite different architectures doing good work efficiently. Would that be okay?
We're definitely always open for cooperation.
Excellent. Thanks very much.
I love that. You come up, you speak, you ask a question, you get assigned action items by people in the community. All right, cool. So I think we are now right at time. I could take one last question if we have any. All right, cool. Well, thank you very much again.